Right at the end of the last lecture, I touched on the notion of a main connective. Um, Maybe this notion is intuitively clear to you, but it's probably worth thinking about. Paul Teller goes over this in his book. You can also find out about it on other online resources. Um, but here's the idea of a main connective. Here's this complicated sentence, and it's got lots of connectives in it. It's got 5 different negation signs and an or sign. But the idea is that no matter how long or complex your sentence is, it has to be built up in the right sort of way from bits. And so there's a connective that has to be, as it were, applied last. And in this case, it's clearly this negation sign here. The parentheses help to indicate that, right? We've got a negation applied to this P. We've got 3 negations applied to this P. But then those two things are combined with this or, and finally, it's this not that's placed at the end that completes the construction of this sentence. Okay. Similarly, this sentence has a horseshoe and a wedge, but it's clearly the wedge that connects the Q and the R, while it's the horseshoe that is the main connective, binding the P to this conjunction. Okay. And in the final sentence, it's the not that's the main connective. So that's certainly something to be aware of. It's vital to understand that when you are deconstructing sentences using this tree method, because you have to know how to deconstruct long sentences, right? And you have to know to treat this sentence here as a negated disjunction, right? Whereas this is an implication, and this is a negated implication. Okay. But if you understand all that, and you understand how to use the decomposition rules for trees, then it's really pretty mechanical. You can show that in fact this set of sentences is indeed inconsistent. Okay, so let's see if we can do that. Notice, right, here's our 3 sentences at the top of the tree. Notice that the negated disjunction and the negated implication will not have branches, whereas the implication will. As a general rule, we'll see this a little bit later, but as a general rule, it's better to leave the rules that involve branching for the end. Okay, because the more branches you do now, the more you'll have to reduplicate your work on each of those branches when you decompose later sentences. Okay. So you want to sort of try to save that for the end. So I'm going to start with the decomposition of this negated disjunction here. And if we do that, we get not P, and we get not P. Okay, that's decomposing this sentence here. I've written a little check mark here to show that we've decomposed it. Okay. Well, that gives us a double negation, so let's go ahead and get rid of that. In fact, we've got 2 double negations, so we can use our double negation a couple times, our rule, and we get down to P and P. Okay. All right, now let's go after this thing. This is a negated implication, and we know that when we have that form, let's go back and look at it. Right, we need we write down the antecedent and the negation of the consequent. Okay, because both those things must be true in order for this negation to be true. Okay, so in this case, here's our sentence. So we're going to write down the antecedent, which is not R, and the negation of the consequent, which is not Q. Let's go ahead and get rid of that not Q and replace it with Q. Okay, well, we're getting somewhere. We don't see the incompatibility yet. We're down to P, not R, and Q. No problem so far. But we still have this other sentence here. Okay, and that's the one we need to decompose now. This is an implication. In order to do that, we need to have a branch. We write down the negation of the antecedent on one branch and the consequent on the other. Okay. The Q and R, of course, can itself be decomposed, so let's do that here. Okay. And now we're done, right? Now we've decomposed every complex sentence. The only sentences left on this tree without check marks next to them are P, P, not R, Q, not P, Q, and R. Okay. Now we just have to convince ourselves that in fact these branches close. If we look at the left branch, we've got not P, but also P. That's no good. And if we look at the right branch, we've got R, but also not R. So that's no good. Okay. And so indeed, this is a closed tree. And so indeed, this set of sentences with which we began, even though it's long and complicated, by using a fairly straightforward method, we have shown that, in fact, they're inconsistent. Okay, cool. Of course, not all trees will close. Some trees will stay open. So if we have, for example, P or Q and Q or R, well, there's nothing incompatible about that. There's nothing that says we can't have both of those sentences be true, right? In fact, all we need is Q to be true, right? P and R could be anything, and both of those sentences would be true, no problem. But to show that in a tree form, well, we're going to have to decompose each of these sentences. They're both disjunctions, so it doesn't really matter with which we start. Suppose we start with P or Q. That will look like this. Now, we've got a little bit of an issue here. We need to decompose Q or R. Where do we write that? Well, we have to put the results on each open branch. We have to decompose it twice, so to speak. Right? And this, again, is why we want to save the branching rules for the end, if we can. Right? But the idea is, well, we know that Q or R has to be true, but we don't know if they're, as it were, true here or true here. Okay? So there's a branch for each branch. Right? If P is true, then either Q or R has to be true. But on the other hand, maybe it's Q that's true, in which case, well, still, either Q or R has to be true. Okay? So we've decomposed a disjunction on top of a decomposed disjunction, and that's why we have this reduplication of branches. Okay? And again, there's no closure at all, right? Either we have P and Q, or we have P and R, or we have Q, or we have Q and R. Okay, no problem. Okay, to push you off and lead you to start trying to tackle these things on your own, there's an exercise page for these truth trees on the home page. I want to illustrate one more thing about these trees, which is that sometimes some branches will close and others will not. Sometimes some branches will close before you're even done decomposing your tree sentences. And so this example will illustrate that. All right, so suppose we start with not P, P or Q, and not Q or R. Okay. Well, if you look at these sentences, it's pretty clear that they're not, in fact, incompatible. However, not P together with P or Q means what? Well, it means that we'll have to have Q true. Right? Since it's not P that's true, it must be Q. And since it's Q that's true, that affects this sentence also. That means that R must also be true. Okay. So in fact, you could use these sentences to prove that Q and R are true, or that the sentence Q and R is true. I'll leave that as a challenge for you. But let's go through with our true method to show that in fact there's no closure. Okay, not P, P or Q, not Q or R. Well, we have these two sentences that need decompositions. Both of them, unfortunately, involve branching. We'll just start with the P or Q. So here's P, here's Q. Well, the left branch is closed already, right? Because P already contradicts not P. So we'll just go ahead and close that branch off immediately. And now when we decompose this sentence, we don't have to worry about the left branch. It's already dead. It's already closed. Okay? So we have not Q or R. Let's decompose that. Now we'll not worry about the left branch, and we'll just place the branch under this node here, not Q or R. Well, that middle branch closes too, because it's got not Q and Q. Okay? But this branch here is still open. And if you'll notice, what's on that branch is what we said before, that Q and R must be true. Okay. Maybe not immediately obvious given these sentences, but if you sort of stare at it long enough, you can see that this not P will force Q to be true, and that in turn will force R to be true. Okay, and that of course is indeed the one branch that stays open on our tree. Okay, good luck. The exercises will look like this. They're all fairly straightforward. Some of them are harder than others, but really it's the same task every time because the rules stay the same. Okay, just keep using the rules in the way that's detailed here, and you should be fine. Okay.